Thank you. Welcome here today. I'm Maarten Scherjon, working at VI Technologies. I've been working there for the past 8 years, and I'm a CLA. Actually, just became in COVID times, which didn't allow me to go to all the CLA conferences and nice things, but GDevCon is really nice to be here. I'm a software architect there. I'm working on the LabVIEW node, as I call it myself, but it's a bit of a quick clickbait title. So bear with me. So I put together an Our Giants Are Female slide on Suzanne Rogers. She actually has the same profession as my hobby. I like to do live sound engineering. And she's actually a fully self-made sound engineer. She started off as a night receptionist in the University of Sound and Arts because she couldn't afford the education herself. So she took all the books and started learning herself. Until she saw an help wanted sign for an audio and industries corporation in Los Angeles as a maintenance tech and started working there. From that way on, she started working on tape recorders, and from there she actually started in Ruby Records as a studio maintenance tech. And when she was working there, she was once working with a guy, 24 years old, who later turned out to be Prince. So she was the actual sound engineer working on his albums. Doing the actual Prince albums and started working with really big artists. And now she actually got her PhD in music cognition and psychoacoustics from McGill University. And she now teaches at the Berklee College of Music. So she's a really self-made scientist, which I liked in the profession that I also liked. So back to the presentation. Why am I actually giving this presentation? So to answer the why, I think it is an I. INI is actually building on communicating to other languages. They started building nodes to communicate to all other languages. They built so much that I actually start thinking that they don't like LabVIEW anymore. But I think, and that's also a nice power, that they actually communicate to all kinds of devices, all kinds of hardware, all kinds of cameras, serial devices. And I think that's the real power of LabVIEW that we explore each day. Using all kinds of different hardware. So to go a little bit to the why in the project sense of the way, we got a project which actually had a hardware setup. It was consisting of stage control, camera control, and some measurement output. I think that's your usual application that we built. But the actual users were a bunch of researchers. They have the actual system knowledge for the experiments. They analyze the output data, they interact with the software. So this is the software that I was building. But those researchers actually transferred to using Python for the last couple of years. They came from MATLAB, started using Python to do image data analysis from the results coming from my application, and started to do like more image analysis, data-driven correlations, and they wanted to have actually scripting access to the application that we were running. And at first, that was really small interfacing like scripts. So what we actually got is from somebody else, got a little piece of code which actually could click buttons on a VI with the TXT file as an input. So from Python, this generated a TXT file which can then click buttons in LabVIEW. But as you can understand, that's really one-way communication. If something goes wrong, nobody knows. If it goes wrong somewhere in the middle of the night, nobody knows. It becomes a TXT file of 40,000 lines. How are you going to debug? So that became a problem. So this was not scalable at all. So we went to look for a new solution. So the start of the journey to look for a new solution actually started at what do we expect from a LabVIEW interface? What do we want to give our customers as Python users? But this actually translated for me to the question, what do I expect if I get a hardware device, or if I get a camera or a function generator from one of our projects and I want to implement it? What do I expect to get as an interface? So to start this search, I have a little bit of an interactive part of this presentation. I actually want to know what you like as an interface. So on the left, we have option A. The VI tree driver, I think we all know it, right? You get a hardware device and there's a tree driver that we can download from the tools network. It has a lot of inputs and outputs, a lot of VIs that you can use. And on the right side, option B, you just get a manual. They say, here, I have a device and a manual, good luck with it. And you have to implement everything yourself. So a little bit of a raise of hands. Who likes A? Who likes B? I guess so. Yeah, there's still some favorites. I can question that, but okay. So let's do the thing again. We are evolving, right? We are evolving. So on the left side we have the VI3 driver again, and on the right side we have a Modbus interface. So as you can see, this already improves, right? The communication is abstracted away. We still have to do some programming for ourselves, but it's getting easier. Again, hands for A. Nah, we're going down. Hands for B. Okay, okay. A little bit of a questionable there. So I think what I actually said already, the communication is abstracted away, but I think it still doesn't meet like having a strict API. You just have to fill in registers and check what you actually get out. You don't know what you're getting out. You have a manual and you have to check the manual again from what am I actually measuring. So I'm still not satisfied. So the third and last example here, on the left side, you can guess already. On the right side, .NET interface. I think it already improved again. So hands for A. Still hands. Hands for B. Again, some hands. So I think this one actually improved over the Modbus one, and I can tell you why. Because this actually already has a strict API, right? We know if we have to fill in strings. We know if we get doubles out. So this improved over the Modbus example. We don't have to think about how to serialize our data. But still, I think there's improvements to be made, right? We still have to look into documentation. If we have a method that says next value, what does that do? What does it give me? It gives me a value of what? So I think there's still things to improve. And I think actually the left part is not that bad at all these properties that I just called, right? You don't see decommunication. All serialization happens inside the method. You get a strict API out. So if we summarize this, what do we think of what do we expect of an interface? I think we can actually summarize this into a few, let's say requirements for our interface. The main one being encapsulation, I think, and it encapsulates the communication. So it should, as we said, encapsulate the communication, encapsulate the serialization, so how to translate our data into the data type that we want it to be. Encapsulate the implementation or the scope, so that we actually know what to execute, right? If we get a method, we want to know what we are actually executing, and also abstract away methods that we don't need as a user. And then comes, I think, the strictly typed API, right? We want to know what types of data we want to fill in. We want to know what types of data we get out, and how to use that method. Together with that, I think, comes documentation. So, with this I don't mean the manual, because the manual nobody looks at, right? We get a manual, we throw it away, and we try it ourselves. But I mean the documentation that you get with your code, right? If we look at the VI, reading the VI documentation, the VI description, maybe some documentation with the controls, that's easy. We like documentation in our native language. The next part is the error handling part. So what we also like is to have error handling in our own language, right? If we get a VI that says get error and you get a number out and you're like, what is this error? So I think having error handling in your native language, if we get an error on our error wire, having a code, having a description, having a source, we can actually debug. We can actually find out where the error happened. So I think this is also a really good specification for our interface. Then a few quotes that actually apply to having the requirements to your interface, which one of them I think is pretty generic to software requirements, right? As simple as possible and as complex as necessary, which I think generally applies. And the second one is actually one that I got from an intern at our office. I was working on this presentation, working on some code, and I asked her, like, what do you expect from an interface? Just as a random question, and this was her answer. It has a clean look and does what you want it to do. Fairly simple, but I think also straight to the point. Even though she didn't have the context, she still knew, still gave an answer that was valid, even in the LabVIEW language or any other language. So what now? So this is all relating to if we, as LabVIEW programmers, want an interface to actually program other devices. But if we want other programmers to interact with LabVIEW, we want them to have the same type of experience, the same type of interface. So I started looking at what matches our expectations, our requirements, when communicating to LabVIEW. So I think a lot of these topics are already mentioned today. We will see some that we already have seen today. I think the first one being the LabVIEW CLI, which doesn't meet these requirements at all. You can execute LabVIEW with it. That's about it, right? I don't know what kind of method, I don't know what the inputs or the outputs are. I have no clue. I have to do everything in like command line stuff. This is not an interface I want to give to somebody else. So then I think the next two parts, I've actually built this upon the knowing of last year's GDevCon, where there were also two presentations interfacing to LabVIEW. One made a TCP IP interface and one made a web service interface, which I think both concepts are not bad, but they don't fulfill our expectations. They don't fulfill our specifications. The TCP IP is nice as a communication layer, but doesn't do the other things. The web service already gets a little bit better because it has names for the methods, it has an interface about what you actually want to program, but still does not comply with having an API in your native language, doing error handling or documentation even. So this led to the design or the search for a new tool, something that I could not find in things that I already knew. So this is the part where I have to make a big disclaimer. I did not invent this. A colleague of mine did, Patrick Bruins. He's from the Netherlands. If you know him, and if you don't, send him a message that you like this. But he is the actual inventor of this code and the actual developer of the base layer of it. I just asked him nicely to use it in my project, and from that point on, redeveloped it to actually be the project that I'm presenting today. And I asked permission, of course. The design actually is for Python calling LabVIEW, right? From this point on the presentation on, we're going to talk about Python calling LabVIEW. What is actually the design that we want to incorporate there? So I think the base layer should be the communication, right? We already discussed that. That's the basics of how we are going to communicate between the two languages. Then there's a layer of serialization, how to transfer the data and the data types of the native language to the other language. And then comes the strict API, the part where we as programmers interface to. We want to develop that in LabVIEW so that we know what the other side can actually access, and we want the other side to have an API also in their native language to actually access the data that we expose to them, or methods or functions. So this is the way LabVIEW or Python calls LabVIEW. So from this point on, it only works this way. So then the actual LabVIEW design, what did I implement? What did I work on? And we start in the middle, the communication part, as we discussed, the lowest layer in the tree. So we started on searching what kind of tool works, and I think for this, ZeroMQ worked really well. ZeroMQ is a standardized protocol known in the world, and it has packages for all kinds of environments, including LabVIEW, made by Maarten Scherjon. It has a package also for Python. It also has a package for Linux RT even. So this is a well-standardized protocol that we could use on this side. Then on the right side, we have the serializer, the serialization layer also. I actually did that two implementations. I think the main way is JSON. It's a well-known serializer for getting data types from LabVIEW to JSON. It also is a well-known package for Python. So this was an obvious choice. I did two implementations, and I can also tell you why. Performance. So we tried out the JKI one, and we tried out the James Powell one. I'm not going to tell you who won. I do tell you who won, James won. But that was mainly for performance reasons and in the application that we were building it in. So maybe on another part, JKI wins, but this was what it is for our needs and our use case, the best choice. And then on the left side, this is actually where the magic happens. It's the executor. The executor is the part that knows about how to call those functions in LabVIEW. So we want to expose something that we already built. We want to expose a method or a function dynamically, and the executor knows how to call that method. So if you look at the LabVIEW side, how is the design on the LabVIEW side? The LabVIEW side has the communication layer waiting for a message. It waits for the message, it gets the message, deserializes all the inputs that it gets from the JSON, actually calls the method in LabVIEW, deserializes or serializes its outputs of the method, and then returns the message to the calling language, in this case Python. So this is the V model of the LabVIEW execution. I think fairly straightforward. If we would take this, and the call method part is the interesting part, and we would set this next to how we would do this in Python, then we get to this example. So this is also the example and the demo I'm going to give you in a minute. But if you would look on both sides, so on the left we have LabVIEW, the LabVIEW project. On the right side we have the LabVIEW functions.py file. So they should match. And what you can see here is that we actually tried matching that. So on the left side we have the communication, and on the right side we also have the communication as the import 0 and Q. On the left side we have the serializers with the JSONs, and here we can also see we import the JSON. So then actually we get to the class. So the console class is the class that we're going to expose today. So we're going to get that into Python and going to call methods of that class. So here we have the console class. It actually, you can see it has the same methods as which we have here on the left side, the clear, the get lines, and the print. And the print function actually accepts a line. It's a string input, and you can print the line. So yeah, this is the basics of, we want both sides to do the same. That's the base part, right? And so how do we make sure this all matches? And that relies on a few key concepts actually in LabVIEW. One of them being to find the connector pane. So the connector pane is the actual API to our method, to our function. So if we want to know how to translate or communicate with LabVIEW from another language, we need to know what the actual API is. So this VI actually finds out what is the actual API of the VI. So left top in is the VI reference to the VI that we want to expose. We get the connector pane out. We get all the controls on the connector pane and the actual pattern that it uses. And the pattern is important, as you can see in the top image, because the pattern actually explains where the connections are. And because at VI Technologies we do a lot of object-oriented programming, we use the Goop toolkit for all our object-oriented development. We know certain places are reserved. For example, the left top is always the class input, the right top is always the class output, the left bottom is always the error in, the right bottom is always the error out. And those are the numbers that you can see in the static array on the left bottom side also. So in that way we can actually find out our statics. And those are things we are not going to expose to Python, because that's not the actual interface to the method. The actual interface to the method is the line, the string input that we want to find. So probably that is somewhere on 10 or 9 or whatever. So what this VI then does is check all the controls that are on the API and check what the index is of the control. So this is a different number than the number that it is on the API, because that number is actually the number that LabVIEW keeps in the backend for all the controls on the VI front panel. So there's just, I think they're ordered by the time you place them on the front panel, so that just doesn't know. And we get to know if it's an indicator or a control, because we want to know if it's the input API or the output API. And then there's some things for descriptions. That's mainly regarding the documentation. I won't go to the full right side of the VI, but you can get the gist. This gets all the information about the VI you want to expose. The next big part in this functionality, how this works, is actually Did You Know from VI Technologies. I don't know if you follow us on Twitter or Instagram or somewhere else on social media. You've probably seen these come by. There's the get and set control values by index. As you know in the previous slide, I got the indexes of all the controls, and that's actually to make these methods work. And why are these methods important? Because they can actually interface to my VI without having the strict data type needed. So I can actually set all the control indexes with an array of variants in. So I don't have to know the exact data type that goes in there, as long as it matches with the control that is on my front panel. So, and that way I can also get, of course, the outputs out. So I feed it all the indexes of the output controls or output indicators, and it gives me all the values as variant array for all those indicators. So in this way, we can actually interface to the method without knowing its strict data types, and we can actually transfer the data from our serialization layer to the VI in a very easy and efficient way. So if we implement this actually into running a VI, we get to this. Left top, the method says get method info, which just gets all the information that we just previously figured out from the connector pane. And it actually feeds that to the set VI inputs. VI, that's the set control values by index method. You get the VI reference in at the top. You get the indexes in at the lower input, which has the class in index. Like I explained before, we do a lot of object-oriented, and that one is separate from the control indexes because that is actually the API. So the class index gets actually matches the build array that is up top there, where the variant goes in at the bottom, and the class wire actually goes in at the top. So that matches that index. And then the inputs that comes from the left is actually the input to our API, our VI API. Then we actually run the VI and wait until it's done. Okay, done. And then we actually get the VI output. So we use all the indices. We get the error out index, which was also an output that I discussed that was not actual API, but we use it separately, and the indicator indices. So that's actually the API again. We get the error. We get all those values as variants, split off the error, and use the error for error handling, and the outputs as the actual output of our API VI. So these are the two concepts in LabVIEW to actually create, to actually run the method that we want to expose. But then comes the side of the Python, right? We want to give our users, our people, an actual interface. And how do we build that interface is with scripting. So this is not LabVIEW scripting, just to be clear, no blue VIs, nothing there. But Python is a text-based language. We all hate that. But it actually looks a lot like a format into string, right? So we can just script entire Python files just with a format into string. So that is actually what this module is doing. It takes all the information from the executor, which had all the information about how to run a method, all the descriptions, all the inputs, the outputs, but gives it to our scripting VI, which can script it into Python, and then generates actually the LabVIEW functions.py file that you saw before. That file is not touched by a programmer, it's totally scripted. So if you look back into our example, on the right, I'm going to come back to that. So if you look at how you would use that actually, this is actually the live demo. So on the left top, we have the 0MQ client, which is actually going to run our communication layer and start waiting for the message. And on the right side, we actually have the Python code using the LabVIEW functions.py. So if we're going to run this, you can see that I start the LabVIEW part up, and it actually brings up the console. So that's the console class just bringing up its process. And then I run the right side, which runs the Python code communicating onto the console on the left. So as I say it there, well, let's rule the world together. So LabVIEW, or Python in this case, actually calls LabVIEW, calls the print function several times, as you can see on the right, and communicates that string to our console. So if we go back to the slide that I already showed you, I can actually now say a little bit more things, like the console class is scripted, like I showed you. But with that, we can also script the documentation. So this line of documentation is actually the documentation of the LV class. The documentation that is within the print VI here is actually the documentation that I added in my LabVIEW VI. I can even add documentation to my controls, saying the units or saying what you can fill in and what you can't fill in. And it will also get printed here. The whole parameters and return stuff is all scripted by what I know from the API. I also can then script, of course, the inputs and the actual outputs. So below here, we actually bring the parameters in together with the actual execute method, which is here below. And we say to LabVIEW, so this actually communicates to the LabVIEW part, saying, I want to execute from the console class the print function with all the parameters in this case, only the line input. And the result is actually the parameters out, which this method doesn't have, but you can bring up an example that does, and the error. So that's why I also split off the error wire, because I want to do something separate with the error as a LabVIEW programmer. Because like I discussed in our requirements, we want to actually handle the error in our native language. So I do the same here. The LabVIEW error actually gets parsed if there's an error, so if the status is true, into an exception, a Python exception. And that's their native error. So that's their native error handling. So if you look into the LabVIEW functions.py a little bit closer, it has some more classes that actually go for general functionality. So in this case, for example, the class which is a LabVIEW error, which actually inherits from exception. That's how it works in Python. So a little bit of a class in Python. And then, so there's an explanation on the base class for LabVIEW errors, and as attributes we actually get the sources like we also have them in LabVIEW, right? Our source, or our code input, and the source input that we also know from LabVIEW, but that the Python programmer can also use to actually see what happened, what actually went wrong in LabVIEW. And also there defined actually how to print this as a string. So LabVIEW error occurred with the code blah blah and the source being blah blah. So the second part of the LabVIEW functions.py file is the remote call class. I'm not going to explain you this all. You can forget this, but this is actually the base layer where we communicate to LabVIEW. So we have actually two methods here which are important. One is the connect, which actually makes the 0 and Q connection. So this is where you can actually see is actually our communication layer. And then here I made a method to execute the method in LabVIEW, which actually uses, as you can see here, the JSON dumps, and here the JSON loads, which actually does the serialization. So if you implement this well on both parts, the LabVIEW side and the Python side, you can actually use the LabVIEW functions.py as an actual interface being the same as your LabVIEW interface. Then there's the top level class, the LabVIEW control class, as I called it in Python. This is actually for wrapping all the functionality of the communication and the abstraction away so that the Python user can just statically call the console class. So this opens the connection and brings the connection to all the classes that actually that we can call from Python. So then the example file. So this is a bit of a closer look into the example file that I just showed you in the demo. So at the top, you can actually see I import the LabVIEW functions as LV. So that imports the whole LabVIEW functions .py file. We actually create the class instance for the LabVIEW control class so that it opens the connection and brings that connection to all the other classes. And from that point on, we can actually just call lvc.console, which is our class that we want to call, .print, which is the method we want to call, and then feed it in a string in, just like the interface is in our LabVIEW code. And I didn't have to do any programming to get this working in Python. So yeah, a bit on to the summary of the presentation and what not. So a few considerations, things to consider when using this, because I built this for a project. It's not perfect, of course not, but it works. I tested it, I demoed it here, but I also am using it actively in projects, also improving it actively in projects. But that's still that's up for grasp. So the front panel must be a memory. The get and set control values by index function works with the front panel. It interacts with the front panel. So if you remove the front panel in build time, the function will error out. So you need to include the front panel or in the build spec. It's a check mark there. Or if you use a property node with a front panel item saying like, for example, a label text or something, you just get it, put it in a case structure that doesn't run. It's enough to actually include your front panel into your build. Also, all published methods must be reentrant. Yeah, that's just how the run VI works and the open reference. There are now our selected collector panes, our layouts are supported. So the 686 and the 4x4 is implemented. That's just because we use those. Selected data types are tested. So I tested this with all normal LabVIEW data types, so just Boolean strings, numerics, all clusters and arrays. And if you go to these arrays, you can actually in Python use the NumPy arrays. So the JSON dumps and load actually knows how to handle that, so that's nice. Also enums I found out worked recently, but you have to fill in strings in Python instead of the actual enum value. So you have to make sure that, for example, in your documentation of that method, you say what the options are and which number connects to that. Then your Python programmer is probably fine. So yeah, if you find out any strange data types that you want to share between the two, yeah, it could be rusty. It's classes only at the moment, because that's actually how our programming works. We do object-oriented programming. So you can actually just insert a class and expose it, but it works with classes only at the moment. And it's synchronous blocking communication. As you saw, the run VI method just runs, So if you call Python to LabVIEW, the method for some reason doesn't end, you're stuck at the moment. So that's just how it's implemented currently, and I want to give you these considerations. I actually saved this slide a little bit because you can see it from a way back in my presentation when we were looking for what actually matched our expectations. I found out that gRPC is a real thing. I actually discussed it with a few people today already, and I started using it more. I think Peter also was using it already. So I think this could actually replace my code entirely. I'm being honest. But yeah, we were working in LabVIEW 18, and while we started on the project, this was not a thing yet. So I think it's really something to keep up with and to check out. Yeah, keep track of in the more upcoming times to how it's going to be developed and also implemented by NI and used. So this is something to keep an eye on. And then the summary, why should you use it? Of course, it's a strict bi-directional API for your application. You can expose it to the world, expose your world to Python programmers. As you probably have seen, we also did one for MATLAB programmers, which also works. But yeah, maybe you can think of other languages that actually use 0MQ and JSON and do the same thing. It's cross-platform and multi-language. So yeah, we do Python and MATLAB. We tested this also on RT Linux. So for example, your LabVIEW code runs on RT Linux and your Python code runs on a Windows, and they just connect the 0MQ over the network. Could also be a really interesting application. And there are still some possibilities left. As I said, the code is not perfect, so I think we can even use it as inter-LabVIEW communication, like James Powell was already discussing, for communicating between different executables, running both a bit of the same code in LabVIEW. You could actually really easily integrate it as inter-LabVIEW communication. I think it should be fairly straightforward to actually support LVLibs. You don't need to handle the class input wire, and you need to get the methods like a different way than we get them from classes, but I think it should just work perfectly, which I think could be interesting for the DQMH people. There can be other types of communication or serialization. If you like another communication type over the 0MQ, you could actually do that. Of course, this is a request-reply mechanism, which is synchronous, so it needs to do that. So for example, the MQTT example, I don't think it will fit because it does publish subscribe and not request reply. But you can think of other things. Also, other things, types of serialization don't come to mind, but you could. And of course, add other connector panes. And yeah, as a basics, it is actually up on our GitHub page at VI Technologies, so it's free to use by all of you. It's called the Remote LabVIEW Interface. We also wrote a blog post on it on our website about this interface if you need to get a little bit more background knowledge. I put the 2 links here. I will also put them in the Discord chat of this presentation. This is actually the blog post that we wrote about it and the GitHub page for actually downloading the code if you like it or contribute to it. As I said, it's as is. Maybe not in all places very nice. Yeah, I think this is actually my presentation. So yeah, I hope you liked it. And if there's any questions, I'd like to hear from you guys. Any questions? I see there and Neil there.
Hi, I do have a question. What's the performance overheads? Because I'm expecting some kind of latency.
Yeah, so I tested this. So with the Hello World example is also a performance example that I put in there. Yeah, there is overhead, but I think the main overhead is actually in the translating to the JSON part. So if you do that for very large data sets, we tried it for an image, I wouldn't recommend. Because the JSON part just takes up the most of the time, actually. It's not the communication itself that's pretty, yeah, what is fast, what is slow, but in the millisecond range, or also for executing the VI, doing the set control values by index, those are actually more performant than the local, I have to say that correctly, the property value set property. The get set value by index is actually more efficient than that one. So I don't expect any overhead there.
Cool. I also had another question. In one of your examples with the prints, you had a couple of sleep statements, I thought.
Yeah, yeah, those are just for having the nice little window pop up in the demo. That's just for waiting, so that you could actually read the lines when they were popping up. Nothing more, nothing less.
Cheers.
Thanks.
Hey, Maarten. Neil here.
Yeah.
Great presentation. Thank you.
Yeah.
I was lucky enough that a colleague attended the DUTLUG a couple of times ago, where this was presented.
Yeah.
And he told me about it, and we actually started to use your repository. And by the way, it just worked straight away.
Thanks.
It's fantastic. Really, I'm just so grateful that you guys put it out there, because we're now building a whole framework like a Python sequencer using this tech, and that set get index thing with the variants.
Yeah.
That was just the bit that I was kind of. It was just awesome when it was shown to me. It's just like the magic sauce that pulls it all together, right?
Yeah. Thanks.
And we've really made it sing and dance, and like performance-wise, it's unnoticeable. Like you can. Sub-millisecond.
Yeah.
And actually, your statement about it might not work without classes, we've extended it so you can call any VI. It doesn't have to have the class right at the top.
Okay. That's nice.
Yeah, I'd love to show you what we've done as well,
Yeah.
because it's incredible. I'm
Really,
again just so grateful to you guys.
Yes.
Thank you.
Thank you. Yeah, it's really nice maybe to check out the collaboration a little bit. Yeah, I haven't had the time or the will at the moment to implement the code more, because I actually indeed started. I uploaded this when I did a DUTLUG presentation. I think the day before we uploaded it to the GitHub repository, and I tried this presentation a little bit out in our Dutch LabVIEW user group. So if any Dutchies are still here and not attending the user group, this is a plug also. I tested the presentation there, and I'm glad to hear that it actually works. Yeah, really
cool.
nice.
We brought in some actors in Python using the Piker package, and it just works fantastically for like actors in Python and then actors in LabVIEW.
Okay.
And it's awesome. So yeah, let's catch up tonight over beer.
Yeah, definitely.
Cool.
Definitely. Thank you.
Yep.
Oh, yeah.
Hello.
Yes.
Good presentations. Just one question. When you run the VI with that VI server execution node, will that not execute as a top-level VI, and will you not have problems with queues dying? It's just like you press the run button. So how did you get around that? Do you need to create a daemon process beneath the VIs to get this working, or?
Yeah, you're totally right. I forgot to mention that in the considerations, I think. But thank you for mentioning. Yeah, we actually had that problem indeed. If you create a class in the method, because it runs top VI, it just closes all the references when it's done. So how did we overcome that? Indeed, in the class that I was actually executing, I added a process indeed, and just made the method send a message to the process and wait for the return. So in that case, I just relayed actually the message to a process that was still running and will always run. So I solved it that way. But indeed, you're totally right. References will die at the end of execution. Yes, created ones at least. Other questions? Haven't seen one. Oh.
Hey, thanks for a good presentation. You might have said it and I might have missed it, but would it be possible to build an exe and have like a Python API to LabVIEW exe file?
Yes, this also works in build.
It works,
definitely.
Okay.
But you have to take into consideration the things that I already said in the beginning, like you have to bring in your front panel and stuff like that. But the whole code actually works in the runtime environment also. Yes.
Yeah, that sounds like a very nice way of packaging up something to share with someone that wants to interact with it through Python.
Yeah, definitely. We are using it that way indeed. Although the connector pane methods say they are blue, but they execute in the runtime environment. I don't know why, but it happened. Tested it, works. Yeah? Any other? I think it's it.
Cool. Thank you, Maarten.
Yeah.